So mod 2.6 is basically the distance formula, and then I'm going to show you how the equation of a circle can be derived from the distance formula. So let's take a look at the first problem. It says that you are considering renting a house that's located in the intersection of D Street and 23rd Avenue. So if you look at our picture here, there's D Street, there's 23rd Avenue. So that's why they've put the little marker right there, okay? The closest cell tower for your cell phone provider is at the intersection of B Street and 20th. So that's why they put that marker right there. It says each street is located 1 mile apart. So we're going to count by ones. So we consider each one of those 1 mile. So let's put a little thing to remind us of that. It says if you are farther than 3.5 miles from the cell phone tower, you will not have good reception. So in A, what we're pretty much doing is trying to determine what quantity or what quantities do we need in this context to determine if we're going to get good cell service. So what are some things we need to consider? Anybody think of what we need to consider? Yes. We need the side lengths. And when you say side lengths, which is a very good way to think about it, describe to me what you mean so then I can mark it on the graph.
Like the 2 miles
from B to D, right?
From B to D.
Okay.
And then from 3 miles from 20th to 23rd.
Now, if we know those side lengths, then what can we do that will help us determine what what are we really trying to determine then? SOHCAHTOA. We're even down further than that. Let's talk about the Pythagorean theorem. That's what we want. So what do we have to determine? We need really the distance between the two locations. And one option is Pythagorean theorem. SOHCAHTOA, we'll get to that in our next semester, but that would be more helpful if we had to consider somehow angle measures. And since in this case we're only determining side lengths, we don't have to go to that just yet. Okay, so let's put a little line between the two. So you can see here that we have formed a right triangle. Okay, so the next thing says to determine the distance between the cell tower and the house. What the Pythagorean theorem says is that of a right triangle, the sum of the squares of the legs of the right triangle will always be the hypotenuse squared. Remember, that's always the longest side length, the side that is across from the 90-degree angles. If any of you are fans of the movie Wizard of Oz, the Scarecrow, when he gets his brain, tries to recite the Pythagorean theorem, but he actually says it wrong, which I think is so funny because he just got a brain, but he's not good at math. So he says the sum of the sides, the sum of the square roots of the sides. He says square roots, and it's not. It's a square. Anyway, I had a little trivia there for you. If you take a look at part B, we can use the Pythagorean theorem. If we can form a right triangle, feel free to use that. But let me give you a formula for distance that uses the different point locations, okay? So the distance formula that you want is the square root of. Now, you're going to see that it's derived from the Pythagorean theorem, but it's, if we know 2 points on any Cartesian plane, it's going to be x2 minus x1 squared plus y2 minus y1 squared. And we're going to take the square root of that. You might also recognize those values we've done before. That's going to be the change in x squared plus the change in y squared underneath that square root, okay? So you can think of it in any context that you want. Okay. So now that moves us on to part C. Now I know we can't see it right now. You can see it on your paper, but for part C, let's make this into a Cartesian plane. So let's call this 0, 0. So the cell phone tower would be at point 2, 1. The house would be at point 4, 4. Now, because these are mile grids, if you were using the Pythagorean theorem, that has a length of 2, that has a length of 3, so 2 squared plus 3 squared, take the square root, okay? So for the Pythagorean theorem, because we can just count them out in their perfect values, you can just do 2 squared plus 3 squared has to equal the distance that we're looking for squared. So that's 4 plus 9, or 13. So our distance is square root of 13. But what the formula we have down here helps us with is if those visuals aren't there for us, so we don't even have to draw a grid. If we just know that one of them is at 0.21 and one of them is at 0.44, we can apply the actual distance formula. But we should get the square root of 13 each time. So let's apply the formula to find D. So we're finding the distance. We're kind of doing C and D at the same time. So anyway, let's use our formula. So our first point, and I usually go from left to right. I did that before when we were doing some other applications to find our delta x and our delta y. So that's x1, y1. And then let's use that 4, 4 point as x2, y2. So really, we don't even need a picture if we know the point's location. Now let's plot them into the formula. The change in the x's are going to be 4 minus 2. The change in y's is going to be 4 minus 1. Which is, guess what? Magically 2 squared and 3 squared. If those become negative, please keep them in parentheses so that you remember to square that negative. They'll always become a length, so they'll become a positive. And so that is the square root of 4 plus 9, or like we saw before, the square root of 13. Okay? So either way you slice it, that's square root of 13. Now, here's the thing. If I told you that the distance between me and the cell phone tower is square root of 13, that doesn't tell you much. Now, think about numbers we do know the square root of. The square root of 9 is 3. The square root of 16 is 4. So it is 3 point something. I would say it's probably a little closer to the 4 than it is the 3. But let's check. If you were to calculate the square root of 13, we get a value that this is approximately 3.6. Now, whenever you round, I like you using the little approximately wiggly equals. It's just a matter of convention in a math class to tell me that you have rounded something. But if you put it equal, I'm okay with that. Follow any instructions as far as how you are rounding. Remember, iMath tends to like exact values, so they might just want square root of 13. Okay? So we've kind of done C and D, but now I would like to take and do E. So it says, if the point xy represents the position of any house on the grid, explain what x minus 2 and y minus 1 stands for. So if we are at some point xy, and now we are at some point x2, y1 minus 1, the minus 2 is saying we are going to the left 2, and here we are going to the right 1. No, I'm sorry. We are not doing any of those things. The y value, when you subtract 1, it takes it down. Now, we're going to discuss eventually transformations of functions. Transformations of functions, you have to be careful if you do a transformation inside of a function. It is not instinctually just if you subtract something from the x, it will go to the left, and if you subtract something from the y, it's going to go down. When you do it directly to the point, it does give you something a little different than if you actually do something other than that. I mean, so just be careful. In this particular case, when you do it exactly to the point, it does what you think. If you're subtracting on the x, it's going to move it left. If you're adding to the x, it's going to move it right, left and right. You know that. Y's are going to move up and down. Okay, so that's a little bit about that. Now, I'd like to look at F here. It says, use the expression in part E to define an expression that represents the distance of any house located at XY from the cell phone tower that's located at 2-1. So if we want an expression that just uses XY, we're just still going to use the distance formula. Usually we like to keep the x and y as positive things. So we're going to make this the ending location. So let's make that, our x2s are going to be replaced with just a plain old x. Our y2s are going to be replaced with a plain old y. And then this will be our starting position at the cell phone tower. Okay, so plop it in. So that is going to be x minus 2 squared plus y minus 1 squared. So then it says a new tower is scheduled to be built at some location, H1, V1, and they haven't really given us an exact location. It says define a formula to locate the distance from any house in miles from this third cell phone tower if the house is located at XY. So again, we have 2 points, XY and H1, V1. Again, it is customary, just like before, let's leave our X and Y to be in the positive location, so our ending location. So let's make this the X2, Y2, and this the X1, Y1.
Attention teachers, the warned students will be returning from their meeting at this time. The warned students will be coming back to their class at this time.
So let's take and plop these in, okay? Again, you want your X and Y to be in the positive location. It doesn't really matter because of the fact you're squaring it, but it is helpful. Okay, so let's plop these things in. So the distance between the new cell phone tower and any house is going to be the formula we're going to get by creating it from the 2 points. The one referring to the house XY, the one referring to the new location of the tower. So let's plug those in. So what we get is X minus H1 plus Y minus V1 squared. Now, what's cool about this new formula we've created is if we pick any house on the grid, the point xy, wherever it ends up, its exact location. We can plop it in. Once we know where the new cell phone tower is going to be located, wherever that H1V1 happens to be, plop that in. We can always find the distance. So then it becomes this general formula for the distance between any house on the grid and that particular cell phone tower. They might call a different cell phone tower H2V2. That's another new one. Or H3V3. They will sometimes alter it a little bit for that particular location. Everybody good with F and G and how I got those things? Do we have any questions? Okay, so now we're looking at number 2. It says, consider a cell phone tower at the location -2, 4 on the given grid with a radius of 3. So let's just make a little marking here, just for reference. Let's mark that our radius is 3, which we can also consider the distance. Okay, so the distance from the center is always 3. Okay. The positive vertical axis is north and the positive horizontal axis is east. So we can pretty much see that. So this is, let's mark that. That's north and that's east. And that is traditional as far as how that goes. So we could even say, we could put a little mark, since most of our circle is in that northeast-west boundary, okay? So north is positive, east is positive, west will be a negative y for future reference, okay? Okay, it says the point x2 is southeast on the service boundary. So what do we know about that? 2 is always our y value, so it's somewhere in here. The x is an x, okay. What must be the value of x? So think about the fact, if our y value is always 2, our x value is either this one or this one. Now let's figure out how we can actually do the calculation, okay. So let's use our distance formula to hit the circle perfectly. The distance is always 3. Let's plug in what we know. We know one of the points, the cell phone tower, is at -2, 4. So we're going to call x2 our x1, y1. We're going to call -2, 4. No, that's going to be our x2, y2. This one's going to be our x1, y1. So let's plug it in. Okay, so it's going to be x plus 2, because we got to always subtract that x1 value, plus the quantity of 4 minus 2. Let's make sure I got that right. Okay. This is why I label them. Okay, so we made this x2, y2. We made this x1, y1. So yeah, I did have this switched around. Can you switch this around? Let me show you how I knew I switched it around for future reference. Okay, I did it again. I so wanted to get a positive number. Okay, there we go. Sorry about that. Okay, how did I know I switched it? And in this formula, it fixes itself if you make that mistake. But the x and 2 go together. The 2 and 4 go together. So that's how I kind of saw I was making a mistake. So let's think about something. How could I get rid of the square root to make this problem instantly easier? What could we do to get rid of a square root? What is the opposite of that? Yeah, so let's take and do that. Let's square both sides. because the opposite of square rooting is to square something. And so we get 9 is the junk inside the square root. Now let's do this number here. 2 minus 4 is -2, but when we square it, we get 4. Okay, now that's a solvable equation. You might recall back in the day, you are able to solve it. Okay, so let's go ahead and do that. Subtract a 4 from both sides, we get 5. Now let's go back up and look at the numbers we're looking for. So our y value, or our height, is 2, right? Remember, see, our height, our y is 2. So we know it's going to be, now I'm going to hit the spots on the graph. So I know it's this spot, and I know it's this spot. See how they're not good spots? So we should expect to get a funky decimal of some sort. Now, what's going to get rid of a square? A square root. Now we are inflicting the square root, and on the grid, we can have positive values standing for east. We can have negative values standing for west. So the reason we get a 2 value option is because you should put a plus or minus on the square root. If you inflict the square root, you put a plus or minus on it every time. And what we get is that plus or minus the square root of 5 is equal to x plus 2. Now let's move that 2 over by subtraction. We get that just always shove it in the front of the plus or minus symbol. That's what I do to make sure that I don't mess up. Now, the square root of 5 is a number just super close to 2 point something. So that makes sense that if we take 2 point something and subtract 2, that's this little value right there. And then if we take -2 and we subtract -2, we got just a little bit over the -4 spot. So it makes sense. So let's do the 2 values that are an option. Now it says, okay, so it doesn't really say if we're going to be on the east side. That I was looking to see if did they want us on the east side or did they want us on the west. I don't think they've said that. So I'm good with you stopping there. That is a correct answer. We could use an x value of -2 plus square root of 5. Or we could have an x value of -2 minus square root of 5. Now, 1 is approximately, let me tell you, this top one is approximately 0.2. That's the one we saw right here. That's when you're east of the tower. And then this one here is approximately -4.2. That's this point right here where we're west of the tower. And then that leads us to our bottom one here. It says if we are at any point on the surface boundary, so on that circle, create a formula that represents any point on the surface boundary if our cell tower is located at -2, 4. So all you got to do there is leave x, y as our positive one, so x2, y2. And then let's leave -2, 4 as our x1, y1. So we think of the center as our starting location. And then plop it in, and then we got it. So the answer is x minus a -2. So that's going to become a positive. It's always going to switch sign in that formula. Plus y2 minus y1. And that will always be the distance that any house location will still get that cell service if it's 3 miles away. Okay? So anything within the service area, That's the maximum distance of anything in that service area, okay? If we know the distance is 3, we could put the d there as 3. That would mean we're on the border. If we wanted to be inside the service area, it would be a number less than 3. But that's a little bit about how we could make a formula. You're going to see this square root, squared, and squared in any type of thing related to distance and circles. Distance and circles, you may not have thought about it, but they are related. The definition of a circle is all points that are equal distance from a given center point. And so it makes sense that distance and circles go together. You just might not have thought that, in the past. So we're done with this. Please turn this in at this time.